This isn't just a mushroom.
Thank you to Display for supporting PBS. One day, as part of a...
Hello. Well, you heard him right. And you're hearing me. So you know that there's something to be said about this. And it is... Duh. Have you ever heard of nucleation points? Hot water moves those around a lot easier than cold water. So if you've ever seen ice that has been, and I literally gave a comment saying, you know that saying about flash freezing liquid, and then you move it, and suddenly the entire bottle of ice of water has turned into ice. Do you know why that happens? One crystal forms, and then the rest of them follow suit. Well, what happens if you're actively trying to freeze something and it has some energy to it? Well, guess what? Now that one crystal is forming multiple crystals everywhere on the outside and is able to flow inside, and so all of those points can spread simultaneously from different areas inside the bottle. It makes it freeze faster. Now, why is that so hard to understand? Because hot turning into cold doesn't make sense. Hot turning into frozen just makes no sense. The amount of cold that you have to put in order to make something turn from hot to lukewarm to cold, all that process, everything makes sense the other way around. But if you already know the function of flash freezing, this makes total sense. Let's watch it anyway.
Cooking class. A boy named Erasto Mpemba was given the assignment of making some ice cream. He boiled some milk, added some sugar. That's probably about enough. Then he poured that mixture into a container. Of course, he had to wait for it to cool before he could put it in the freezer.
Do you know why you have to wait for it to cool to put it in the freezer? Glass doesn't like to expand suddenly. Bitch. So you literally better put it in something that doesn't mind that ice turning into ice, or the molecules inside of the glass turning into ice. Because you just got a hot thing, put it in a cold thing, it better be resistant to those strains. Otherwise, yeah, you could have broke your dish, dude.
Who has time for that? I want ice cream.
Question is, what kind of container did he put it in? And what kind of container is he using right now? Because I don't think that the glass is going to be happy about it.
That day in 1963, Mpemba was in a hurry too, so he put his hot ice cream mixture in the freezer while it was still hot. Now his classmates left theirs out on the counter to cool first before putting them in the freezer. But later, to everyone's surprise...
What if you just stir it first? Or put a little magnetic stirry stick inside of it? It doesn't have to be hot, it just has to be moving. Huh?
Even though everyone else's mixture had started at a lower temperature, Mpemba's ice cream mix froze first, faster than everyone else's. All of this happened at a secondary school in Tanzania when Mpemba was just 13 years old. When he found his oddly expeditiously frozen treat waiting for him the next day, he could have shrugged it off as some sort of fluke, a weird, unexplained event. But he didn't. Instead, he asked why.
So of course you gotta know that I've already seen this entire video, yet I'm reacting to the entire video, because of course, you know me.
That question turned out to be a lot harder to answer than anyone expected.
Why?
60 years after the ice cream incident, physicists are still arguing about this phenomenon.
Why?
Now, a appropriately called the Impemba effect. Maybe you've heard about this
Called
trick
flash
before,
freezing.
but what you probably don't know is how this strange observation, watching hot water freeze faster than cooler water, has begun to shake up very different corners of physics, from how we heat and cool machines to how we design materials, even quantum computing. Today, we're going to dig into this deceivingly simple phenomenon to learn why taking the longer route can sometimes be faster. After I finish my ice cream. Hey, smart people.
I bet you
Joe
that
here.
wasn't fluffy.
It turns out that 13-year-old Erasto Impemba wasn't the first person to notice this. Scholars have been pointing out this weird effect for thousands of years. The first known reference came from Aristotle. Doesn't it always? It was all the way back in 350 BCE. He wrote this book called Meteorologica, in which he mentions how in certain places it was common practice to heat up water before freezing it. He points, for example, to ice fishermen in Pontus, in what's now Turkey. They would pour hot water on their rods because it freezes quicker, and then use that ice to hold them in place. Over the centuries, the effect was noted again and again by scholars. Here's one from Roger Bacon in the 13th century, or René Descartes in the 17th century. Lots of pretty smart people have been fascinated.
Nothing to do with the salt in the system, right? It's because the ice cream was identical in both scenarios. Unless you use more salt, there's no difference, right? Yeah, there's a little salt in ice cream. What are you talking about?
By this. And historians have since found numerous accounts of people around the world making the same claim. Hot water sometimes freezes faster than cooler water. But all this seems to go against our intuition about how heat works. So people have been pretty skeptical of claims like these. Some even...
Is it sometimes, or is it because of salt?
outright dismissing them as flawed experiments. When Impemba asked his physics teacher why his hot ice cream froze first, he was told, "That is Impemba's physics, not the universal physics." Skepticism is a good thing, of course. It's a necessary ingredient in science. But luckily, that didn't stop Impemba. Years later, a physicist named Dennis Osborne visited his school, and Impemba asked him the same question. Of course, his classmates laughed at him, but Osborne didn't. He went back to his lab and ran the experiment himself. He got the same seemingly impossible result that Impemba got, and they published it together, with Impemba as first author. My name is Erasto B. Impemba, and I'm going to tell you about my discovery, which was due to misusing a refrigerator. Let's take a second to appreciate how weird.
It's not misusing the refrigerator. Again, the container, if glass, doesn't like it when you put it in the freezer. So that's why you put it in when it's less temperature, because then the glass will be able to be okay. But if it doesn't have that issue, like, for example, plastic, or for God's sake, styrofoam or something, cardboard, metal, you might have better results. Or something else that is like, it's freeze safe. But I don't know what's like that, like quartz crystal or something?
This actually is. When you freeze a cup of water, it cools continuously from room temperature down to freezing. If you start hotter, you've just got farther to travel before getting to freezing. So it should always take longer, right?
If you think of hot and cold as just the motion of the doodad, then the moment that the doodad turns into a crystal that is capable of being a nucleation point, all of that motion is the flash freeze effect. It's gonna happen faster.
The This was captured in Math by Isaac Newton in his Law of Cooling from 1701. It describes how things change temperature continuously. Compared to a room temperature glass, a hotter glass of water will drop in temperature faster at first, but then it'll just trail behind the other glass as they keep on cooling. I mean,
well, that's because at that point they're both at that same rate. They're both at that same amount of energy or whatever else. There's no more motion that can be put into it. It's already slowed down, made into a crystal, into ice type mush or whatever. So there's not much else you can add to it to make it go colder faster. At that point, you're just turning a slow thing into a slower thing.
That makes sense, right? Picture two curiously handsome runners racing to a finish line. One starts closer to the line, the other one starts way back here. Obviously, the one that starts closer to the finish line wins, right? Well, that's not always the case. Sometimes the runner who starts farther back crosses the finish line first, but only if he runs the race in a very certain way. That's the...
When my parents come over to my apartment, they have to go up a set of stairs and around, sort of, one little bit of hallway, and I end up going the other way, which is all the way to the end of one hallway, around the stairs, and back a little bit. I run the further race, but because my legs are longer, or because I use more steps per second, whatever, they're not bad off, but I'm always ahead of them. That's not hard to do.
Pemba effect. It's actually not hard to show that hot water can freeze really fast. On a super cold day, throw some boiling water into the air and it'll instantly freeze into these beautiful icy rainbow shapes. If you try that with lukewarm water, just get cold rain. But it has turned out to be incredibly challenging to demonstrate the Mpemba effect rigorously and repeatedly in the lab. In the decades after Mpemba and Osborne published their paper, physicists had attempted to replicate the effect, with honestly pretty mixed results. I mean, some studies seemed to replicate the findings, but others directly contradicted them. Now, there are two big reasons for this controversy. One reason is that these experiments are really tough to control perfectly. Like, whenever you compare when two liquids freeze, what tips that balance to one or the other can be so many things. The shape of the container, dissolved gases, how smooth
Atmospheric pressure,
or rough the surface is, or if something disrupts a supercooled liquid,
how does snow...
even tiny ice crystals can start a chain reaction of freezing. There's an absurd number.
That kind of thing, but imagine the nucleation point is throughout the entire thing. Because it's all moving. You don't just get one crystal growing, you get all of them growing. I can't believe you even mentioned that.
Of variables to control. The second reason is that water itself is very weird. It's actually most dense at 4 degrees Celsius, just above freezing. So as it cools, the coldest layer sinks and warmer water rises to the surface, where it evaporates faster. Once ice does actually start forming, those crystals float and insulate the water underneath, slowing the heat loss back down. Water is just surprisingly strange stuff. And for that matter, what does freezing even mean? Is it when the first ice crystal forms? Or when the average temperature hits 0? When it's fully solid? Different labs have used different definitions and gotten different answers. This is tricky stuff.
Obviously,
so maybe the Mpemba effect happens just because water is uniquely weird.
Things with other freezing levels.
Not quite. Over the last few decades, that exact same signature effect, starting hotter and getting to frozen faster, keeps showing up in materials that they have nothing to do with water, which means that whatever's going on is bigger than just one strange liquid.
The new Michael's Rewards program,
I'll be back.
Which means that whatever's going on is bigger than just one strange liquid. Take these molecules, for example. polylactic acid, or PLA. It's what many compostable cups are made of. And if you got a 3D printer, you almost certainly use this stuff. But to form it, you have to get the molecules to crystallize. They lock into an ordered structure, which is sort of like freezing. And guess how you can get them to freeze faster? By heating them up first. But it gets even weirder than that. The effect doesn't just apply to temperature either. You can find a magnetic Impemba effect too. If you look at the magnetic field of certain materials, you'll find that objects with a stronger magnetic field can be demagnetized faster. Again, winning the race by starting farther from the finish line. It seems like the Impemba effect isn't some one-off quirk. It's a real feature of nature.
What if it had to do with the energetic nature of electrons or something? And reactions are more likely to happen with more energy. So more bumping, more sharing, more something else. And once that starts happening, they can't help but share. And a faster, anytime you have faster conductive material, you end up with a bigger amount of electrical. I'm sorry.
Another thing.
That was a face. But anyhow, you end up with a bigger amount of electricity made. So any generator running faster is obviously going to power the light bulb faster. That's why when the person, when the person's on the bicycle and they power the light bulb at the science fair. But in a microscopic level, and whatever, you end up with stuff going faster also. And it's like, really, why wouldn't you? Does someone end up looking at it in a microscope as it's doing it?
Thing that they all have in common, the more extreme it is where you start, the faster you can find your way back to equilibrium. A state where everything is settled and stable, done changing. You see, nature loves equilibrium. Leave out a cup of ice in a warm room.
The thing about crystal formation is that it has nothing to do with equilibrium. It has everything to do with all the energy that it wants to have is like to become that one structure. It's actually holding itself in place with all the energy that it has. I think you could freeze things faster just by having it move. Just by having turbulence. Not just one motion of like stir it first, but like bubbles. So imagine if you aerate water while you're trying to freeze it. What's it gonna do then? Slushy?
And eventually it melts. It settles at the same temperature as the room. A leaf falls onto the ground and eventually it'll decompose and become indistinguishable with the soil. Everything, given enough time, ultimately seeks out sameness. Why does the world crave equilibrium? Well, it's simple statistics, really. Basically, there's just many more ways for things to be randomly mixed up than to...
It could also be that anytime that you input energy into a system, like with an orbiting planet system, there is pull on the upswing and pull back on the downswing. These forces kind of equalize. So similar thing can happen maybe in atomic physics, in the fact that the more you have certain amounts of, well, I mean, that obviously wouldn't happen because of gravity is what drives it in a planetary thing, so it's not the same function at all, but
to stay clumped together. The lukewarm water is vastly more probable than an ice cube. Mixed up soil is more probable than an intact leaf. So what does this have to do with Impemba's ice cream experiment? Well, inside of a freezer, the equilibrium state is, well, frozen solid. Both the hot and cold cup of water are racing to that finish line. The question is, how does the hot cup get there first if the cold cup has a head start? Does it somehow want it more? It turns out, well, sort of, yes. See, scientists have worked out a mathematical explanation for this shortcut. They showed that the fastest path to equilibrium isn't always the most direct one, especially when systems start with more energy. Imagine firing a ball into a maze. The harder that you shoot it, the more that it can ricochet around and maybe find a path to the target. A system with more energy and more things inside jittering and moving in all sort of quantum atomic-y ways, they can explore more pathways to equilibrium, potentially finding faster shortcuts along the way. Picture the road to equilibrium as a downhill journey. For a ball that starts here, it'll roll sort of sluggishly to the finish. But for a ball that rolls from here at a higher energy starting point, it has more energy to carry it to the end faster. If there
Depending on the rate of gravity.
are intermediate valleys along the way, the faster ball might be able to find shortcuts to the lowest energy state. That's how it reaches equilibrium faster.
We need to not be esoteric about this, please.
Is equilibrium faster. One group of scientists tested the effect by building this energy landscape in real life. And when they dropped tiny glass beads into this landscape, they could stop at this first energy hump, or they could roll through that first one to this more stable resting place. They found that the beads that started out hotter tended to find the lowest resting place faster, just like the math predicted. And it goes even smaller than that. Down at the scale of
Yeah, that proves the idea, sort of, but not the mechanism.
individual atoms, physicists have found a quantum version of the Mpemba effect too. Picture a row of trapped ions, kind of like tiny compass needles, all pointing the same way. That's a state of symmetry. Now, tilt them out of alignment. If you just leave them alone, they'll eventually drift back into sync. But if you tilt them further out of alignment, sometimes they snap back into sync faster than ions that were only disturbed a little. Physicists confirmed this quantum Mpemba effect in the lab for the first time in 2024. And this isn't just a curiosity. Researchers have started using this exact effect to quickly reset the memory in quantum computers. It's sure starting to seem like this is all the same beast in different forms. From freezing ice cream to wiping out magnets to quantum alignments. Now, across all these different materials and different scales, there's one consistent theme. The shortest route is not always the fastest one. And we still don't fully understand why the Mpemba effect happens in every case. But that hasn't stopped people from putting it to work. Physicists are already exploring Mpemba-inspired tricks to make cooling and heating systems more efficient.
That's
which,
cool.
Not a huge surprise. But Mpemba is turning up in some much weirder places too, like improving the manufacturing of ceramic materials. Now, some very special ceramics have to be compressed really tightly to be formed. Instead of using a big squish machine, one group used the expansion of freezing ice to squeeze the material. And sure enough, they found that the freezing happened faster if they started with hot water. Thanks, Mpemba. Who knows where else Mpemba will show up? I mean, that's the beauty of discoveries like this. You start with this tiny little oddity, something that doesn't seem quite right. If you keep poking, you might end up exposing a new way of looking at the world. In this case, the mystery comes from assuming that everything is close to equilibrium. Whether or not we realize it, much of our intuition about the world is built on that assumption. I mean, we imagine that the air in a room is exactly the same temperature everywhere. We assume that flipping a coin 100 times will land us exactly 50 heads or tails.
I know that over at the window it's cooler than over at the stove, because the air is being actively cold at the window. At the stove, it's less because it has less stuff going on about it. Less energy being put into the system. More stale blah. More energy put into the system, colder. Just saying.
Nails, or that the balls in a ball pit are randomly distributed by color. But if you think about it, the things that are far from equilibrium are often the most interesting. Take fire. If you leave it in an empty room, it'll eventually peter out and just blend in with the air. But if you keep feeding it oxygen and fuel, if you keep pushing it out of equilibrium, it can light up your room, even drive your engine. And you and I and all life as we know it, we're all out of equilibrium too. All the work that we do in the world is only possible because we draw energy from the sun and from our food to constantly push ourselves away from equilibrium. When we fall into equilibrium, we die. We decompose.
Well, mostly.
Blend in with the soil, just like that leaf. Far from equilibrium is where all the exciting stuff happens. But it's also where our intuition about the world kind of goes out the window. It's where nature can play all sorts of surprising tricks on us, like the origin of life, or earthquakes, or the Impemba effect. This story is a wonderful reminder of the power of questioning the world around us, even things as trivial as a bowl of ice cream. You never know what it'll turn up. New questions, faulty assumptions, deep insights just hiding in plain sight. I think Impemba and Osborne put it best in their very first paper about this effect. No question should be ridiculed. Everyday events are seldom as simple as they seem.
I remember some bitch talking about, oh, if you're one person and you have an idea about the world and you say everyone else is wrong, you gotta be out of your mind and dumb. This is just one example of how one person can change the entire idea. Yeah, in a way. It's not the first time this has happened, as he said. But one person can bring up an idea that was otherwise just sort of in the background, not really looked at deeply, and it made it spark. Blue LEDs, another spark. Other such things, another spark. So when I fucking tell you, motherfucker, when I tell you electrons do orbit around an atom, not a regular orbit. It is 22 quadrillion times the width of an atom is how fast an electron moves. Right? 22, or I should say 22 quadrillion atomic width per second. How wide an atom is, it does that 22,000 times, 22 quadrillion times per second. It's a million billion. So, if you want to hold something like that, it can't be some random chaos. It's an orbit. But how does that orbit actually look? It looks like the diagrams. It comes in phases. It's constantly shifting slightly to the right or slightly to the left just to avoid itself so it can keep on moving. It also goes up and down in the many different layers of shells that it orbits in its area. Well, many different fractions of a shell. A shell is meant to be the entire orbit of an electron, but that is actually many different components of that region are where it has moved. So imagine the electron has to go around and around and around and around And all those different directional ways that an electron can go around an atom, it does literally every second. Because if you think about how many times it can go around something, and then it ends up going around again and around again, you repeat those kinds of processes a quadrillion times, it's going to look like a random cloud that's going in all sorts of directions. That's why it's extremely hard to pinpoint where the actual electron is in its orbit. Because any specific individual part is 1 quadrillion frames per second. Out of another 22 quadrillion frames per second. You gotta find where those spots are, down to the femtoseconds. And you're not gonna do that easily. But it doesn't mean that it's not going in that basic orbit. It's just that that orbit repeats so many times faster. You have persistence of vision, you have echo, remnant electromagnetic effects, and the beauty of like what we end up seeing in the diagrams.
Or, in other words, stay curious. Hey, before...
Yeah, this video is Oreo. Anyway, if you then... Other things like time dilation. I'm going to stick with it and keep telling you time dilation's a hoax until you understand it. Because unless I can be absolutely convinced, I am not changing my perspective. Because I am not wrong. Now, what does it take in order to understand time dilation? The speed of light, the speed of the orbit of the rotation of the Earth, and the speed of the planes in that one experiment that I know of. That's all I need.
Here you go. We are really excited to tell you that the team over at PBS Eons just finished an amazing new TV show, and it's available now. Eons, Life and Death on Pangea, has everything you love about the YouTube show and way more. The series tells the ultimate story of the supercontinent Pangea during the Permian period.
That's pretty awesome. So, time dilation is a misunderstanding. It's not like they are intending on lying or being mistaken about it. They just don't know any better. And they were so sure about things for the longest time. Just like with this one, for some reason he's not talking about, like he did talk about ice forming crystals, but it's like, yeah, if you break apart those crystals, if they're big enough to form more crystals around, it doesn't have to be a sheet going down slowly. It can be everywhere throughout the cup, expanding in all directions simultaneously. And that obviously leads to greater amounts of freezing. Again, I think if you had the water stirring, it would freeze faster, possibly. So it's like, if you had it in a dish that was spinning, would it freeze faster? Is another good question that people should just ask and try doing. I don't know how you would go about doing that experiment, but you just have to try. Not so fast as a centrifuge, but like, or a salad spinner, which is a centrifuge, but like a basic amount of spin. Or, obvious question, add more amount of motion to the system. At what point does it start, like, at what point does it have the most amount of speed towards the... And that's the other thing. What if you stir the hot stuff? Clearly, that will also include more energy in the system. It's already hot. Now it's also moving.
Time of massive geologic upheaval full of incredible creatures, which all culminates in the greatest mass extinction in the planet's history. Check out the link in the description to watch. Thank you to Display.
So why does flash freezing, that thing we saw in the middle of the video, the bottle, wherever the hell that was, wait, where the hell is that bottle? It's really cool to look at. Is this? Did I pass it? Bitch.
Elevate your practice with trusted solutions.
Tips that balance to one or the other can be so many things. The shape of the container, dissolved gases, how smooth or rough the surface is, or if something disrupts a supercooled liquid, because even tiny ice crystals can start a chain reaction.
Noticing it's a chain reaction, what if, instead of those ice crystals big enough to cause nucleation, aren't part of a bigger system and they're able to freely move throughout the bottle? I think it would just freeze all throughout. Instead of just one layer at a time, you'd have many.
Of freezing. There's an absurd number of variables to control. The second reason...
Of course, the bumpiness is again a nucleation point where it has the ability to cause the ice crystal to form in the first place. A structure big enough that it, when other water bumps into it, it then has the ability to cause more crystal formation. Anyway, fun.
Is that water itself is very weird. It's actually most dense at 4 degrees Celsius.
I am slightly curious. I don't remember if he talked about salt. Because, like, salt will put certain amounts of stuff. Like, you put a string onto some ice cube and put the salt on it. The water around that salt will start to melt and then freeze again, so that the string is now connected to the ice cube. It's a fun little thing you can just do at home. Real easy to do. Don't do it with hair. What the fuck? It's gross. But anyhow. That was a neat fact. I can't say there's been any, like... Okay, I did say, like, don't be esoteric with the... Okay, let me explain to you why I don't like the energy level nonsense. Where the fuck is it? Ball pits. Got some more.
Faster if they started with hot water. Thanks, Mpemba. Who knows where else Mpemba will show up? That's the beauty of the way of looking at.
Where is the there is the energy level nonsense.
That first one to this more stable resting.
Do you even understand what you're trying to explain when you talk about resting places? I don't know if you do. Again, it could be that what if the hot stuff has a greater amount of slight electric field and magnetic field, and so the ability to attract other bits to the crystal is what makes it so that you then have like the slightly higher amount of, like, who knows how that does hot or cold water. Obviously hotter water would probably have a bigger amount of magnetic or electric field, which is like, how the hell do you even check that? And did they check that? I don't think they did. It's like, imagine if you have like a small bead that you put into that super cold water, and then you drop that in. The nucleation points of it going through the water will then spread from everywhere that bead went through. So suddenly it all just freezes in a big line in all directions. Instead of straight down, it goes from the middle outward. And it's like, that is such a neat thing to also do. This is angel hair chocolate. Why? Anyway, that was tasty. Goodbye.